So today I'm going to talk about something a little bit different. It's about how to secure public network with micro-segmentation. This is a joint work with my collaborators, Sathiya, Santi, Ranveer, Leslie, as well as Srikanth. So because of public clouds nowadays host so many sensitive data, it has become a major target for all the cyber crimes. In the past few years, there are a lot of these large-scale attacks that been leaked so much user data, become a major problem. By one estimate, somehow this one doesn't work. By one estimate, the cost of running this cybercrime has introduced trillions of dollars and has surpassed the GDP of many countries. And the traditional solution of this is called ring fencing, where we have a firewall to protect all the network assets within the network. However, if an attacker somehow get to compromise one of those nodes, they will be able to do a lot of damage and steal a lot of data. So instead, a more promising solution has introduced is called micro-segmentation. So this is based on the concept of zero trust. The idea is that some nodes will somehow get compromised. So we create this very fine-grained security policy, only allow certain nodes to talk to certain nodes, so that even if some nodes get compromised, they won't be able to do a lot of damage. And this is actually a big market and also robust growth. And to realize micro-segmentation, the typical workflow is first we have to be able to see who talks to who. So we will collect the flow trace and then to generate these communication graphs. And then the next step is called policy authoring, where those graphs will be sent to those network deployment owners. They will look at those graphs and then create a group of nodes. They call them micro-segments. And then using those micro-segmented graph to create security policy, and then they can enforce them based on runtime graphs. However, to do this at large scale still has two major problems. The first problem is this step of manually creating these micro-segments. Because in large network, those communication graphs get complicated very, very quickly, and not one person knows everything. And so it becomes very hard for them to figure out which nodes should be grouped by which node. And so the other alternative approach is that there are these raw inference algorithms in graph mining literature. And then so we evaluate them on 11 real deployments. And here we use this metric called ARI, is the very widely used metric for evaluate the quality of clustering compared to the ground truth. And then we find them perform actually quite poorly across large scale, especially when the scale gets larger, they get much worse. So the second challenge of this is that these communication graphs have to be continuously generated so that they can be enforced. But this is actually turned out to be a very costly operation because the data we are operating with is very large. So here there are two leading vendors that providing micro-segmentation solutions, and we find them the cost they introduce compared to the virtual machine cost, they introduce 18 to 70% of the additional cost. And this cost make it harder to deploy them widely. So in this talk, we're going to introduce this solution called ZTS, which is zero trust segmentation. It has two major components. The first component is that we introduce a very effective raw inference algorithm that can facilitate this large-scale policy creation much more efficiently. The other component is we introduce this pipeline that can generate communication graph very efficiently, and it can make us generate this low-cost scalable graph at much lower cost than existing solutions. And next, we're going to first talk about the first component.
So we did test some existing raw inference algorithms on our real production graph. And you can see from the results here, they all sort of produce different kind of raw inference results. And more of that, they are all far from the ground truths that we have. So here we find out that with existing raw inference approaches, they are mostly based on these structural features. So for example, with an input graph, you will first extract some structural features. For example, can be how many neighbors does one node have? And then you transfer them into some node embeddings, and then you cluster them and which infer the rows for you. However, these existing approaches, they don't really work well in our cloud resource graph. For example, here in this graph that the same color infer the same kind of row. And just to avoid confusion that the same color with the different shape, they are also the same row, but the different kinds of identity. So here, you can see that if you only count how many neighbors does one node talk to, then the red circle and 2 green squares here, they are actually the same kind of node because they all only talk to the red square here. And that will make them to be clustered into one row, which will be the PC4 here. And after that, with the clustering, it will have incorrect row inference results. So the problem here in our deployment graph is the graph structure, sometimes they can be completely identical. But what we do have in cloud resource graph is we have a lot more information than that. And by more information, for example, if we have one node, if you look at the logs, it might have 1,000 or more features that's associated with this node. However, the problem is, how can we use this information? So first, because there are so many features, we actually don't know which features are the most important. And second, the feature importance, they can also change based on different deployment or based on different scenarios. But what we do have is we have some sparse labels also exist in the graph. So what I mean by sparse labels, it can sometimes be the name, or it can sometimes be some tags that users give us, or it can even be the IP addresses that help us to infer some of the rows. However, the problem here is these sparse labels, they are not complete. So how can we really use them to help us improve the row inference part? And we find an opportunity with the concept of contrastive learning. So the intuition behind contrastive learning is we want to pull the embeddings of similar nodes together while push the different nodes with rows apart. And here's the loss function, but you don't need to read it. I'm going to give you an intuitive example of how contrastive learning works. So here, let's say if we want to find out what's the role of this orange node, with the existing node, we will first have their embeddings, and then we try to calculate their similarity and put them together. So after that, what the contrastive loss can help us is it will try to push the orange node to be closer to the row it is same as, and to be farther with the other rows. So with the contrastive learning concept, we're thinking that maybe we can use these partial labels that exist in the cloud resource graph to help us to refine and guide us through the row inference process. So if you remember, this is the workflow of how existing row inference algorithms do the row inference. So first, what we do is we put all the domain-specific features that we have in the cloud resource graph also into the autoencoder for node embedding. But notice that we're not trying to manually pick any important features. We're just putting them all in the autoencoder, and we'll let the contrastive loss to help us decide which features are the most important. And then second, we want to use this domain knowledge that exists in our graph. And with the domain knowledge, as I said, it can be some IP address or some tags or names that help us create these partial labels. And with those partial labels, we can have the contrastive loss and with the autoencoder to put all three things together and help us learn an embedding space. And furthermore, our system is not one-shot. So with some client feedback on the inferred rows, for example, after we infer the row, client can either help us correct some row, or client can give us more input on some other labels. This will help us improve the system iteratively with more labels. And last, for the structural features part, we actually subsume all of the structure-based algorithms, which means that you can always replace that part with the latest advanced structural-based row inference algorithms. So with this algorithm, let me show you some results on the row inference part. Here we use the metric called ARI, which is a widely adopted like clustering accuracy metric. And first, we test all of the algorithms on some smaller deployments with the node edges rows in the above range. And you can see that ZTS, which is the green bar, is always the best. However, that in this case, the cloud cluster, which is the pink bar, it also seems to perform like relatively well. But if we enlarge the deployments, which when we make the nodes and edges into tens of thousands of them, you can see that cloud cluster in this case suddenly becomes the worst baseline. So here we find that ZTS is consistently the best across different kinds of deployments, with an average ARI reach 0.77, which is much better than other baselines, which other baselines might perform OK on some specific deployments, but not overall. And next, Sathiya will introduce the system component.
Now, I will discuss our experience implementing a cost-effective and scalable solution for graph generation. To ensure widespread adoption, we utilize components that are generally available across multiple cloud providers. We also aim to be highly cost-effective. So we use network flow logs that are supported by most cloud providers. Such logs can be collected using SmartNICs at the host level. So these logs are cost-effective, tamper-proof, even if the VMs are compromised, and can be gathered with minimal disruption to the user traffic. Due to the telemetry, there are two main challenges. The first is structural, since the data is organized as numerous small files, 1 JSON per VM per hour. And the second is due to the volume of the telemetry, where sometimes the number of records per minute can be really large, particularly for highly communicative nodes. And the resulting graph can be large as well, in the order of 100 to 10x to 100x of the number of monitored IPs. So we need several careful considerations in order to keep both the processing time and the cost low. We implement an architecture that consists of two stages. The first, a pre-processing stage that uses scalable compute. And the second is a graph generation stage that uses SQL-based batch processing. This architecture allows us to pipeline these stages, where once we complete pre-processing, we send the data to the SQL processing, and as the SQL processing is running, we pre-process the next batch of data. This lets us flexibly parallelize and scale the pre-processing stage to handle the volume of telemetry. And we also optimize the data to be easily processed by the SQL system, and thus address the structural challenges. We also leverage decades of optimizations that have gone into such SQL processing systems, and we optimize a SQL query using several techniques. We iterate over our system over several versions, and for an input data set from a real-world deployment detailed on the left, the red line in this graph tracks throughput in terms of the number of connection records processed per second, and the green line in this graph tracks latency in terms of the time to process an hour's worth of logs. We see that latency is dominated by the pre-processing stage, and throughput is dominated by the SQL processing, because the biggest improvement in latency comes from the optimization to the pre-processing stage, and the improvements to throughput comes from our SQL optimizations. In total, we improve both throughput and latency by roughly 9x, and we land up with a low-cost solution where the cost is roughly equal to 0.05% of the cost used to run the actual customer workload. We compare our system against a streaming pipeline based on Apache Flink. We choose Flink since it's an enterprise-ready system. compared to systems like Spark, Flink has been shown to perform well for both streaming and batch processing use cases. The systems under comparison use the resources shown here, and it must be noted that the infrastructure is different, but optimized for each of the system. At scale, looking at a data set size of 39 million records per hour, we see that compared to Flink, our system incurs only 1/3 of the cost. But at the same time, we are 7.5 times faster. Hence, ZTS is 21 times more cost effective. I'd like to emphasize that Flink is a general purpose system that is shown to work well across many scenarios, while ours is optimized for our particular use case. We believe these results show the importance of application-specific design and optimizations. So in conclusion, today we discussed why micro-segmentation at scale is a challenging problem. We also introduced ZTS, a novel end-to-end system that incorporates effective role inference for scalable automatic micro-segmentation and also a scalable graph generation system. Using data from real-world deployments, we show the performance of contrastive learning with domain knowledge and also the cost effectiveness of our system implementation. Thank you.